Let's unpack a new paper titled Switch Transformers, Scaling to Trillion Parameter Models with Simple and Efficient Sparsity. What's the core idea here?
The core concept is to rethink the way we scale large language models. Instead of just making our models bigger by adding more parameters to every layer, the switch transformer introduces a new type of layer, the switch layer, that activates only a subset of its parameters for each input. This allows us to create models with many more parameters than would otherwise be possible while still being able to train them efficiently.
This sounds a lot like the mixture of experts models, which have been around for a while. How is Switch Transformer different?
You're spot on. There's a clear lineage to mixture of experts Mo models. The crucial difference lies in the routing algorithm. Mo models typically route each input token to multiple experts, which increases compute requirements, whereas switch transformers simplify this by routing each token to just one expert. This streamlines the process, cuts down on communication overhead, and improves training stability. It's a bit like choosing the best tool for a specific job rather than using a Swiss Army knife for everything.
Interesting. Could you elaborate a bit more on the computational benefits of routing to a single expert, especially in a distributed training environment?
Sure, in a distributed setting, say training across multiple TPU cores, each core typically handles a subset of the model's parameters and a portion of the training data. In the case of switch transformers, the sparsely activated layers are strategically split across different devices, each device holding a unique set of expert weights, which means we can scale the model's parameters with the number of devices without overwhelming the memory or compute capacity of each device, because only a portion of the weights are used for each example.
Hmm, that's really hard. However, routing decisions are made dynamically, aren't they? How do the authors of the paper manage the memory allocation for experts given the static nature of TPU tensor shapes?
Good question. That's where the concept of expert capacity comes into play, and it is a key technical consideration. Essentially, the authors of the paper allocate a fixed batch size to each expert, which is determined by dividing the total tokens in a batch by the number of experts. However, to help account for uneven token distribution, the paper introduces a capacity factor, a buffer, if you will, that scales this batch size to help ensure no tokens get left behind.
Does this capacity factor have any implications on the computational efficiency of the model?
It does. A higher capacity factor means more buffer space, which reduces instances of dropped tokens, those that aren't processed due to expert overflow and have to rely on the residual connections between layers. However, setting it too high leads to wasted compute and memory as experts sit idle.
How do the authors strike a balance and ensure that tokens are distributed evenly among experts?
To promote a balanced distribution of tokens across experts, the paper utilizes a differentiable load balancing loss, which encourages the router to distribute tokens evenly. This additional loss term nudges the model towards fairer distribution, which is a bit like a traffic cop ensuring a smooth flow of traffic.
What about train stability? Sparse models with their dynamic routing can be a bit tricky to train, right? Especially with lower precision formats like the float 16.
That's absolutely real. To tackle this, the paper introduces selective precision training. Instead of using the computationally expensive float 32 precision throughout the model, they strategically cast only the router's computations to float 32 to stabilize training while keeping the rest of the model in bfloat 16. The paper also shows that reducing the initialization scale for the weight matrices was crucial for stability.
Given that switch transformers have even more parameters than their dense counterparts, do you face any challenges with overfitting, especially during fine-tuning on downstream tasks?
Yes, that is a concern. The authors found that applying a higher dropout rate to the experts during fine-tuning, we call it expert dropout, was quite effective.
You mentioned the impressive scaling capabilities of switch transformers, even reaching trillion parameter models. How do the authors manage to train such huge models?
The authors of the paper efficiently combine data parallelism, model parallelism, and expert parallelism. In essence, they are not only scaling the number of experts, but also leveraging techniques to distribute the computational load effectively across the available hardware.
In the paper, the authors also explore distilling these large, sparse models into smaller, dense models. Could you speak to the motivation behind this and the compression rates they were able to achieve?
The idea there is to make these models easier to deploy and is a common technique used to reduce model size in general. The authors demonstrate that with distillation, compression rates of up to 99% are possible while still retaining about 30% of the quality gains. This makes it possible to deploy a much smaller and faster model without sacrificing too much performance.
You certainly covered a lot of ground, from the model's architecture and training techniques to its impressive scaling capabilities and distillation. As we wrap up, could you give us a quick recap of the key takeaways from the switch transformer paper?
In short, switch transformers present a new way to think about scaling language models, offering a path to larger, more efficient models through sparse activation. It allows us to build models with an outrageous number of parameters without a proportional increase in computational cost. There are still some challenges, especially with training stability at the largest scales, but the results are very promising, and it is a good result on a new axis to scale.
And that's all for now. Thanks for this insightful discussion.